Three of the world's most powerful companies are betting everything on a technology that doesn't exist yet: space computing. SpaceX has filed plans with the FCC for up to 1 million orbital data center satellites. The Elon Musk company said that it would operate a constellation of satellites with unprecedented computing capacity to power advanced artificial intelligence models and the applications that rely on them. This is their vision: data centers the size of small cities floating in the vacuum of space. The likely cost to design, build and launch a 1 gigawatt orbital data center would exceed $50 billion US. But why? Why would the smartest minds in technology want to move our digital infrastructure beyond Earth's protective embrace? And does the highly complex reality of building space data centers actually make it worthwhile? The answer begins with power. It has been calculated that orbital solar arrays could achieve a capacity factor of greater than 95% compared to a median of just 24% for terrestrial solar farms in the United States. Peak power generation in space could be up to 40% higher due to the absence of atmospheric losses. This means a solar array in space can provide 5 to 13 times the energy as the same array on Earth. StarCloud, one of the leading companies in this space, estimates an equivalent energy cost of approximately 15 times lower than today's wholesale electricity prices. Then there's cooling. While the ambient temperature of space sits close to absolute zero at minus 270 degrees Celsius or minus 455 degrees Fahrenheit in the shade, it can reach 121 degrees C or 250 degrees Fahrenheit in direct sunlight. The vacuum of space also doesn't allow for heat to be radiated off in the same way as it would on Earth, so much larger, more complicated systems are needed. One vision of a server farm satellite would have 1,024 square meters of photovoltaic panels generating 240 kilowatts. The server farm itself in a 240 kilowatt satellite could be based on 2 racks of graphical processing units, each with 72 GPUs. To get a gigawatt of total processing power would require tightly networking 4,300 such satellites weighing 30 million kilograms in low Earth orbit. But the real driver isn't just efficiency, it's desperation. Local officials have begun to balk at approving new server farms that swallow land, strain power grids, and gulp cooling water. Some tech executives now talk about putting servers in space as a way to escape those permitting fights. The race has already begun. In November 2025, just 21 months after founding, StarCloud launched its first satellite, StarCloud 1. This has an NVIDIA H100, which is 100 times more powerful GPU than has ever been operated in space before. With this, they became the first entity to train an LLM in space, and the first to run a version of Gemini in space. However, this digital gold rush faces obstacles that would make the pioneers of the American West retreat in terror. First, there's radiation. The RAD 5500 processors that are commonly used in space have a performance of only about 0.9 gigafloating point operations per second, GFLOPS. In contrast, the NVIDIA A100, a commercial off-the-shelf chip commonly used on the ground, already achieves a performance of 156 terafloating point operations per second, TFLOPS. The performance of the chips commonly used in satellites and the COTS chips on the ground constantly differ by 3 to 4 orders of magnitude, largely because of space radiation. By some estimates, a single radiation-hardened microprocessor could cost upwards of $200,000 instead of $300 for an Earth-based processor. Current estimates suggest radiation hardening adds 30 to 50% to hardware costs and reduces performance by 20 to 30% compared to terrestrial equivalents. Then there's the minefield. They'd have to safely wade through 6,600 tons of space debris floating around in orbit, as well as the 14,000 plus active satellites. Dodging these would require fuel. Most of the space junk isn't in Sun synchronous orbit and will be hitting the solar panels face on at orbital velocities of several kilometers per second, 20 to 50 times faster than a rifle bullet. The economics are staggering. We estimate launch costs for a 1 gigawatt data center would approximately be 30 to 75 billion US dollars, in addition to our estimated $50 billion of costs to construct the satellites fitted with data center components and solar panels. And when something breaks, getting a technician on site to low Earth orbit today would cost 20 million to 50 million per person, with a 2-person minimum, with charges escalating dramatically if you need to go to the moon. An orbital data center would need triple modular redundancy, running 3 identical systems in parallel. This means launching 3 copies of every chip and memory drive, 3 times the cooling and electricity demand, and, at least, tripled launch costs and capital expenditures. Yet, the impossible has a way of becoming inevitable. SpaceX's reusable rockets have steadily lowered launch costs. Its Falcon 9 rockets decreased costs from around $11,500 per kilogram to $1,500 per kilogram of payload. The next launch system, Starship, is projected to drop that cost even lower, optimistically between $100 and $200 per kilogram. The satellite hardware industry has undergone a quiet revolution in the past decade. What used to require custom-built radiation-hardened components costing millions can now be approximated with a modified commercial hardware at a fraction of the cost. K2 Space is betting this trend continues, making it possible to deploy significant computing power in orbit without breaking the bank. The numbers are staggering. More than $45 billion worth of investment in this sector was recorded in 2025, up sharply from just under $25 billion in 2024. The timeline is accelerating. SpaceX's planned 2026 timeline for Starlink V3 deployment suggests orbital data center concepts could transition from theory to reality within 2 years. However, full-scale operation data centers will likely require initial Starlink V3 constellation deployment, establishing the basic satellite infrastructure with enhanced computing capabilities. Google predicted that launching data centers to space will become cheaper than terrestrial options thanks to free power and cooling by 2035. The implications stretch far beyond technology. As Jeff Bezos commented at Italian Tech Week in Turin, October 2025, we will be able to beat the cost of terrestrial data centers in space in the next couple of decades. These giant training clusters will be better built in space because we have solar power there 24/7. No clouds, no rain, no weather. It has already happened with weather communication satellites. The next step is going to be data centers, then other kinds of manufacturing. For now, it seems like the power benefits of solar panels in space may at best be negated by the current processing abilities, cost, and technological hurdles still to overcome. However, for most tech billionaires, the real problem is legislation and access to power and resources. This is dramatically inhibiting their ability to actually build data centers here on Earth. With the biggest tech companies racing to become leaders in AI, space may realistically be the only option.